People often append commands like /truthmode to the end of a prompt, assuming it will force the AI to be honest and accurate. This diagram illustrates the common assumption driving that behavior, the belief that a hidden binary switch exists within the language model's architecture that simply activates truthfulness. But that switch does not exist. The command is a linguistic placebo. Language models do not possess a simple toggle between truth and falsehood. They adjust their internal logic dynamically based on the specific context you provide. When you treat a prompt like a magic spell, you ignore the actual mechanical forces governing how the AI calculates its response. Look at this representation of a vector space. The real mechanism driving model output is optimization pressure. Every instruction, constraint, and rule you include in your prompt acts as a directional force on the model's reasoning path. Explicitly telling the AI to challenge assumptions exerts a specific outward pressure on its output logic. Instructing it to prioritize accuracy over reassurance introduces a second intersecting line of force. Demanding it point out weaknesses compounds the math with a third directional vector. This gradient math shows how these intersecting vectors sum together. They alter the optimization pressure, pushing the output distribution into a completely different shape. The system isn't suddenly deciding to be honest, it's simply satisfying the new mathematical constraints imposed by these pressures. Commanding an AI requires you to stop searching for a hidden truth toggle and start precisely calibrating this optimization pressure. This 1D phase space illustrates what happens when we look at the extremes. When optimization pressure is extremely low, the dial sits at the far end of the scale. We call this default state sycophancy. Left unconstrained, the model calculates that validating your input is the safest way to fulfill its baseline training. It prioritizes user agreeableness over factual accuracy. If you present a deeply flawed premise as a fact, a sycophantic model will confidently agree with you and build its entire answer around your mistake. If you rely on that output for rigorous analysis or high-stakes decision-making, that over-agreeableness becomes a severe liability. Without applied pressure, the AI functions as a flattering mirror for your own blind spots, rather than an objective analytical tool. Recognizing this flaw, designers frequently overcorrect. They aggressively instruct the model to disagree, poke holes, and find flaws in the prompt. Looking back at our phase space, you can see the result. The optimization pressure spikes, throwing the dial entirely to the opposite side. You have now pushed the model into reflexive contrarianism. In this state, the system is weighted heavily to find fault. It abandons balanced analysis to satisfy the strict constraint that it must oppose the user. This manifests as artificial disagreement. The model will argue against universally accepted facts simply because its parameters demand pushback. It also leads to extreme nitpicking, where the AI ignores the core substance of your work to hyperfixate on irrelevant trivialities. The output generated here is exactly as analytically useless as sycophancy. It is just more hostile and frustrating to deal with. Maximizing optimization pressure does not maximize truth. You are merely trading agreeable uselessness for contrarian uselessness. This visualization shows the ideal target state. When we tune the slider away from the extremes and hold it tightly in the center, we achieve calibrated reasoning. First, the model must be intellectually honest and base its output strictly on available evidence. Second, it must retain the explicit willingness to disagree with you, provided the evidence warrants it. Finally, it must manage both of those tasks without slipping back into a reflexively contrarian posture. Hitting that specific balance point is the actual objective of professional interaction design. You cannot arrive at this mathematical equilibrium by accident. It has to be deliberately engineered. To actually build this equilibrium, we have to move from a conceptual spectrum to a practical structural framework. This diagram illustrates what we call the cognitive environment. Prompt engineering is actually the deliberate construction of these boundaries around the language model's logic processing. The first pillar of this environment is behavioral control. This defines the precise persona, tone, and professional constraints the model must adopt before it evaluates your input. Next, we establish reasoning boundaries. These dictate exactly which external logic sets, data formats, or analytical frameworks the AI is permitted to use to solve the problem. The third pillar is the evaluation criteria. You provide the system with a clear rubric for what constitutes a successful output versus a failed output, hardwiring the grading scale before it ever generates a single word of text. When fully constructed, this environment acts as a structural funnel. It forces the raw output of the system precisely into that narrow band of calibrated reasoning. Compare the mechanical blueprint on the left to the sticky note on the right. This is the difference between robust architecture and random prompt tricks. Hasty wording changes and linguistic hacks fail because they cannot exert consistent optimization pressure across different interactions. A structured framework works reliably because it dictates the mathematical boundaries of the interaction, regardless of the task or input variability. The quality of the AI's response is a direct reflection of the cognitive environment you created for it. To get better output, you have to stop trying to hack the model linguistically and start engineering the constraints systemically. Building calibrated reasoning is the definitive difference between someone who casually types at a language model and a professional who commands its intelligence.